Good afternoon. I would like to welcome all the participants in this webinar. Okay, the title of this webinar is Open Source Tools for Future Power Systems, and the idea of creating this webinar came as a result of the achievements of one European project that INESC TEC is leading, which is INESC. And INESC is focused on the future development of power systems. We know that the decarbonization of the energy system will require the integration of new resources, and these resources, we think about photovoltaic panels, electric vehicles, small storage units to be installed in households, or even in bigger units for the distribution network. So we will have a huge number of different types of distributed resources that will change the way that power system is operated and planned. So INESC is focused on these developments, and particularly in the evolution of the power systems until and even beyond 2050. So the project is composed of three big research lines. One that is related with almost real-time operation of power systems, that in fact ranges from dynamic analysis of milliseconds until minutes, hours. And then we have a planning research line. This planning is for 2030, 40, and 50. And we have a third one, which is about asset management in this future power system with these new assets that will be integrated in the network. So these three research lines will yield in the end different tools, so different power system tools for each of the research lines. And since the beginning, the consortium agreed that these tools should be open source to maximize, let's say, social benefit, and also to maximize dissemination and the knowledge created in the project in INESC. This webinar is focused on two of these three research lines because we didn't have time for more. And in particular, we are focused today on the operational part and planning part. So one of the presentations will be about operation, the other will be about planning. For the presentations, we have three remarkable speakers, two from the University of Manchester, one from LIST, from the Luxembourg Institute of Technology, I think. And they will, the first one, so the speakers from Manchester will focus on the operational part. And I will now pass the word to them. So the first speaker is Alejandro Martinez, so it's known by Alex. It's an assistant professor at the University of Manchester, and he has been doing a lot of interesting work in multi-energy systems, operation and planning. So Alex, the floor is yours.
Thank you very much. Let me first share my screen just to make sure the things are working properly. So now you should be able to see my screen. So as Felipe mentioned, my name is Eduardo Alejandro Martinez Eseña. I go by Alex, as Alejandro, was simpler to remember. I'm going to be presenting some of the work in INESC regarding investment planning, and I'm going to be supported by one of my colleagues, Dr. Andrei Cherkin, who is doing part of a significant part of this work. And the focus here is going to be on, okay, we all like open source tools, but why do we need new tools for planning the networks? We've been planning the networks for quite some time. So what is needed now? What is changing? And one of the things that is changing is uncertainty and flexibility, the connection of these different resources that Philip was mentioning, and also the wide range of future scenarios. Right now, there's quite a lot of uncertainty about how we're actually going to be decarbonizing the energy system. So let us begin a bit with, okay, what is this uncertainty? How is this changing the way we deal with investments? So let's begin with how it was in the past. So traditionally, there was not much flexibility on the demand side. So customers wouldn't have any technologies like solar, like storage, like electric vehicles. Those things were not really happening. So we had a best view of how demand was going to change. And we used to use those, those forecasts to decide how to invest. There was some variability, some uncertainty here and there, but we could handle that with sensitivity studies. So before, there wasn't really, that's how we started. We just, whenever we hit a threshold, we would reinforce the lines, and that's more or less how it used to work. Then we started getting some uncertainty. Some new devices were getting connected, but still not really bearing that much. We could still assign maybe some probabilities, or even if not probabilities, the values wouldn't really be too far off from our best view. So we started doing some probabilistic studies, and then we reach what we have right now, which is like, well, we now have a lot of scenarios. Are we going to be decarbonizing heating and transports? How quickly? Are we going to be using other vectors? Are we going to be using which technologies? There's quite a lot of different scenarios. So, and this is what we call deep uncertainty, when things are widely spread. We don't necessarily, or we can't really associate probabilities to these different scenarios. There is even higher uncertainty, which is basically the unknown, when there is actually nothing we can do about the future, and we don't know how the future looks like. But we're not going to reach that point, at least not yet. We're still hopefully here where there's a lot of uncertainty, but we might be able to do something about it. So once we go into deep uncertainty, there are two things that first we need to ask ourselves. Okay, well, can we make decisions to deal with this uncertainty? Now, are those decisions going to impact what we can do in the future? If not, then we can model them like something like this. So things are always recombining. So it doesn't matter if you go through the upper side or the lower side, you reach the same position. So you could say the decisions don't really matter that much. They might improve our current position, but they don't limit the things that we can do in the future. In reality, when we're talking about networks, we end up with something more like what we have on the right, which is, well, if we start committing to a specific technology, let's say if we start investing a lot on charging for electric vehicles, then it's going to be quite difficult to later on change the technology to, let's say, hydrogen vehicles, because we already invested a lot in the infrastructure. So our decisions matter, and that affects what we can do later on. So the decisions become path dependent. Now that we know that, how do we deal with the system? How does that translate into investments? Well, when we didn't have flexibility before, when things were kind of deterministic, we were focusing on robustness. We wanted to have something that would work regardless of what was happening in the future. As there were not that many futures, or not very, they wouldn't vary too much, we could do something that was performing relatively well under all conditions. It was robust. We used a fit and forget approach. We invested in the lines, and it would work whatever happened. That's now very expensive, because if we have scenarios that are too different, if we want to create something that is robust to all of them, that means we need to invest in something that can work well with a hydrogen future, an electric future, regardless of the combinations of technologies, and that is too expensive. So instead of that, we start using something else, which is, okay, how can we take advantage of these technologies that are emerging? How can we use the flexibility that they offer to customize our systems so that we don't need to invest in a large thing that can deal with anything, but instead with something that can be modified to adapt to whatever is happening, which is much cheaper. So that's why we need new approaches, because based on literature, if we try to plan for this flexibility without having the right tools, we might get some value, like what you have here in the best view simulation, which is showing you, well, yeah, the flexibility is decreasing the cost compared to the do nothing case, but the decrease is not as significant as if we actually used an approach that capture flexibility, like the multi-stage in this case, or real option analysis. So if there is uncertainty, we can cope with the uncertainty with the flexibility, but in order to do so, we need new methods. That's the whole rationale for having these new tools. Now, how does that translate into network planning? Well, the way this translates into network planning is before, let's say, as example, the distribution network. The way we plan the system is we usually put the feeders in pairs. Again, this is distribution. It's going to change a bit at different voltage levels and at the transmission level, but this is kind of N-1 security, although simplified for distribution, which is if a feeder is disconnected because of a fault, we connect as much customers as we can to the other feeder. But because of that, we need to reinforce that feeder. We need to oversize that feeder. How often do we use that capacity? Not very often, because feeders don't really fail that often. Some of them once every 3 years. Some of them have never failed historically, at least not in the UK. So this oversize is expensive and we don't use it very often. But because there was not so much uncertainty, well, we kind of had a single investment that worked for everything, was robust. Now it's not the case because the demand can vary significantly based on the technologies. Now this changes if we have that flexibility, because we could use supply from these distributed energy resources, the technologies that Philippe was mentioning, to provide capacity during those moments when the network needs the capacity. So rather than investing in extra line capacity, heavy assets to deal with all of this, we can use that flexibility to manage those line constraints and minimize costs. So within ATES, we developed several engines. The one that I'm showing here is a simplified diagram of the distribution network planning model. So what this approach does is it's a reformulation of the optimization into what is called a recursive approach. Basically, a recursive approach is a computation that calls itself multiple times. So this approach breaks the optimization problem into a large number of smaller problems, and the coordinated solution of all those problems gives you the solution of the big problem. Now, the formulation is actually quite complex, stochastic mixed integer nonlinear programming. But because of the limited number of options that you have at distribution, because this is the engine for distribution, if we reformulate it as a stochastic formula, it becomes computationally tangible to solve. So overall, it's a reformulation of a problem that normally is quite complex, but by having it as this series of problems, we can actually solve it and we can guarantee optimality. But only for small systems such as distribution, we cannot extend this to transmission, so we use a different approach. And with that, I will pass the presentation to my colleague, Andri. So Andri, the floor is yours.
Thank you, Alex. Hello, everyone. My name is Andri. I'm a researcher at the University of Manchester, working on this European Horizon ATES project. And today I will be presenting some of our recent results about network investment planning tools. But first, let me elaborate a little bit more about the, oh, sorry, Alex, could you please click? I would like to elaborate a little bit more on the flexible distribution networks and actually the value of this flexibility from distributed energy resources. And I would like you to take a look at this small illustrative example, a small distribution network. And let's say that this network doesn't have any batteries, any solar panels, any electric vehicles. it only has loads at each substation. In this case, we usually call this network a passive distribution network because it is designed only to accept power from transmission system and distribute it to customers. And if we will try to consider flexibility of this network, for example, we can build the map of network consumption, as you can see on the right. Sorry, Alex, could you please go back a little bit? Yeah, so the coordinates of this plot is active and reactive consumption of the network P and Q. And we could wonder what is the flexibility of this network. And we will find that actually there is only one feasible operating point showed by this black cross marker. And this is the only point that is feasible for the network. We can deviate a little bit maybe by changing voltages, but overall the network doesn't have any significant flexibility. And we have to follow regimes, we have to follow the laws. But in the next slide, if we add these new resources, battery energy storage systems, solar panels, demand response, electric vehicles, we get flexible units in the network. And I show this here by the blue font that flexible units there are components of the network that have technical ability to regulate their power exchange with the grid, which means that they can increase or decrease their power injections to the network. And now if we take a look at the same flexibility chart or operating envelope of the system, the aggregated network flexibility, we will actually see that there is an area now of feasible operating points. This area depends on many parameters, the number of flexible units, their capabilities. For this simple illustrative example, I put only 2 units in the network. You can see 2 smaller areas corresponding to FU1 and FU2, 2 flexible units, and the green area is the aggregated, we can say combined overall flexibility of the system. So now the system is much more flexible. It can deviate from its original operating point, which can help us to optimize operation and planning of distribution networks even further. However, there are several issues with this flexible operation approach. First, we need to estimate actually these areas of feasible operating points. And we need to do this very accurately because if we fail with our approximations, the operation of the network can be infeasible or not reliable. We need also to solve some voltage control issues, and we need to suggest some market and pricing schemes for distribution, for distributed energy resources, for flexible units, so we know how much power they actually produce and how to pay them. Could you please go to the next slide? Yeah, this is the last picture that I want to show you about the value of flexibility. Actually, it is from our very recent manuscript submitted to IEEE journal. And here we considered the standard IEEE 33 bus test system. It's a radial distribution network. And we placed 4 identical flexible units. Identical, which means they have the same power capabilities. The problem is that they have different cost functions. And then we solved about 15,000 OPFs to see what happens in each particular flexibility request, how each particular regime of this state of this aggregated flexibility is formed. And to explain this briefly, the dark blue color that you see on these flexibility maps shows that one of the units, for example, unit D, produces most of the flexible power. And some other units, for example, A, the most expensive one, it is not activated in many requests. So I recommend you to take a look at this manuscript. You have an archive link here if you are interested in this research. But basically what it shows that we can have large number of flexible units, and we need to coordinate them. We need to find ways to activate the cheapest units. And in this way, we can further improve, further optimize operation of distribution networks. Next slide, please, Alex. Now coming back to the planning tools. The question is, okay, we know that networks are now more flexible. They can deviate from their initial operating points. Operation can be further optimized, but how can we capture this flexibility in the planning tools? And this can be done, for example, by considering multiple scenarios. And the figure that you see on the left is the information that we actually get from our project partners. We consider only 2 scenarios corresponding to active economy and slow economy. And it makes sense. You can see percentage of increase, demand increase, and in the slow economy, load increase is not that significant. In the active economy, it is larger. But these values are not enough to capture the value of flexibility, because if you solve this problem with only two, I would say mostly separated scenarios, you are solving a deterministic problem, because you make separate independent planning decisions for active economy, for slow economy, and that's all. You don't really see the value of flexibility. So what we do in our tools that we develop in ATIS, we start creating path-dependent scenario tree. And as you can see here on the right, we are branching these scenarios even further in each year, in each time step. So in 2030, we have even more scenarios corresponding, for example, to active and then active economy, or active and then slow economy, and so on. In total, we get about 15 scenarios here. Now, speaking about some examples from the project, I would like to show this semi-urban distribution network from UK. This is quite a small example, one of the smallest networks. Total load is about 5 megawatts, 39 lines. There is only one generator, primary substation connected here, as you can see by the arrow, to substation number 5. And this network has 2 feeders, one normally open point showed here as NOP. So as Alex mentioned earlier, this network can be supplied, supplying 2 feeders separately, or they can be interconnected through the NOP to meet contingencies or to further optimize operation of the network. So also about visualization, maybe someone is confused. The size of these circles corresponds to the total load in this particular substation. So you can see where the load is located in this particular network. And now the question is, okay, we go into the future to 2050, sorry, and how do we plan this network? What new lines we build? And could you please click, Alex? Yeah, what I want to mention here, that if we solve these problems straightforward, it is a hard combinatorial optimization problem, can be formulated as mixed integer problem or mixed integer nonlinear problem. And the main issue is that we have a large number of binary decision variables. So for this very small distribution network, we have 39 lines. We have 15 nodes in our path-dependent scenario tree, which gives us almost 600 binary variables. But this is not the end of the story. And if you click, Alex, please. The problem is that we cannot install in any capacity at any line in the system, and usually system operators have a so-called investment catalog, a range of investments, some given values, which means that for each of these values we need to create more binary variables, because we need to select which of these interventions we select. And if you multiply, let's say, by 20 or 26 investment options that are given for the set of networks you consider, you can get easily 15,000 binary variables that you need to consider in your model. And plus consider that you have time-dependent constraints, that if you build a line now, you cannot build it in the future because it's already built, right? So it influences the scenarios in the future. So it's quite a hard problem, and it's hard to solve it straightforward. And in the next slide, I think I say that the solution here that we take in the project is by using screening and clustering modules. So first of all, we select a simplified version of this module to identify which of these possible investments in the investment catalog we choose. And then we make clusters of these investments. Again, this is done to reduce this number of variables in this combinatorial optimization problem. And for this particular network, the situation is not that bad. The screening model says that only 4 lines potentially need some investments. I highlight these lines by green color. And then instead of, again, solving the entire mixed integer problem, we run a recursive function which runs for each year, for each node of this scenario tree, and start passing information to other nodes. And this is why it's called recursive function, because it iteratively solves the planning problem. And Alex, could you please go to the next slide? Yeah, this is just an example for this case from the UK. Those are real scenario multipliers for UK. You can see how demand is growing. And Alex, could you please click to open the planning decisions? So now we can, by solving this problem iteratively for this scenario tree, we can see different planning solutions throughout years and throughout scenarios. And for example, in the worst scenario, when we have the most demand increase, we see how the lines should be updated. One line is updated by almost 2 MVAs. We can see what happens in the scenario of the least demand growth and in some middle scenarios. And by this modeling, we can actually capture the value of flexibility by adding flexible resources here and seeing where the investment actually happened and where we can postpone them by using our flexible resources. So I think those are the main results that I wanted to share. Do you have any comments, Alex? Thank you.
No, thank you. I think we can take questions at the end of the session.
Okay,
so I think we can now move on.
Yes, I didn't mention that in the beginning, but the agenda or the alignment of this webinar will be this first presentation. We'll have a second presentation, and then in the end we'll have about 10 minutes to question and answers. Meanwhile, if you have any question, and I'm talking for the audience, you can leave your questions in clicking in the Q&A button that you have there, and you can leave your questions. In the end, we will try to answer them. Okay, so the next presentation is about tractable methodologies for optimal power flows, both in transmission and distribution systems. And the speaker is Florin Capitanescu from the Luxembourg Institute of Science and Technology, LIST. Florin, please.
Okay. Hello, everyone. Thanks, Philip, for this introduction. In this talk, I would like to share with you some advances in optimal power flow in both transmission and distribution system that we performed here in Luxembourg. So let's go with the outline of the presentation. So basically, we are focusing on the procurement of ancillary services, particularly for congestion management and voltage control by distribution and transmission system operator, and we place ourselves closer to operation, so in day ahead operation planning. At the DSO level, we envision this procurement of ancillary services in a form of a stochastic multi-period AC optimal power flow problem, and we tailor the tractable solution algorithm to solve this problem in an efficient way using sequential linear approximation. So this research work has been led by my ex-colleague Muhammad Usman, who is now working for National Grid in UK. Then at the TSO level, we are framing this into a stochastic multi-period AC security constrained OPF. And again, we try to find out a good tractable solution for it. Both solutions are tailored, so the one for DSO is not the same as the one for TSO. We try to tailor and to take in the best possible way advantage of the characteristic of each network. This research work has been led by my colleague Mohammad Iman Alizadeh. Then I will conclude and move to future works. So when we look into the future, power systems of the future 2030 onwards, so Alex and Andrei very nicely described some challenges the operators will face. The one that I believe are the most critical ones for TSO and DSO also from operation and computational perspective are the following ones. So first, high penetration of a huge amount of distributed energy resources, particularly variable renewable generation. So this at all voltage levels. On the other hand, we have also, we can see an emergence of additional flexibility options like energy storage and what we call flexible loads, but a bit that would be actually more aggregated deferrable energy entities. I will use these terms flexible loads still in this presentation. So as you know, renewables come up with variability and difficulties to predict them. This undermine reliable operation, so this may lead easily to congestion, voltage, and different other issues in both transmission and distribution systems. And operators need to procure energy flexibility, which was nicely described by, again, in the previous presentation, including from those distribution energy resources in day ahead, and then to activate it if needs be in real time. Okay. Now, there are common challenges, I believe, for both TSO and DSO, the computational challenges, basically. So uncertainties, first, uncertainties in production of renewable energy sources. So this involves stochastic modeling. Then the energy coupling in time, that means that we need to model multiple time periods that are linked between them. As you can imagine, if you want to model this problem by a brute force approach, you will get to a huge problem whose size is the product of these two dimensions. It's larger than the problem that are solved today by the number of scenarios that you want to model and the number of time periods. Okay, and what we envision is that the decision-making tools at TSO and DSO must now be able to solve much more complex problem that includes these, let's say, emerging realistic features. And what we are doing, we are focusing on tractability. We believe that best possible way to deal with such big, huge problem is to work through successive linearization. We try to do this for both TSO and DSO problems. There are some assumptions that I need to state right now. So we focus this from still on a centralized optimization perspective. I think this is perfectly doable at TSO level and still doable at medium voltage DSO level. We also at DSO, we assume adequate observability is in place, and we have this, let's say, simpler assumption of balanced operating conditions. Good, let's move to the DSO problem. So how DSO could procure flexibility in a future smart grid to that problem that we formulate. So what we did first, we did a review of the state of the art in terms of existing approaches that could distinguish in terms of the flexibility resource or model formulation. So there are some resources that can be modeled as continuous decision variables, others are discrete. In terms of model formulation, we could have accurate, approximated, or relaxations, okay? And we realized that there are a number of publications that model stochasticity and multi-periods, which is good. On the other hand, there are some that I would immediately rule out, those based on relaxation, because they are unable to provide a feasible solution. There are some based on mixed integer, brute force mixed integer and linear programming, for which we don't have yet the solvers in place to scale properly. And then there are just these two that, let's say, share some features with what we would like to do. For that one, what we would do more is to try to focus on more flexibility resources, especially those challenging based on with discrete behavior. And then we are doing, let's say, better approximation in the sense that we manage to provide feasible solution at the end of the day. Okay. So the challenges, computational challenges for the DSO are that when you go to model this, flexibility options such as storage, flexible load, and OLTCs involve binary variables. So the problems are, as for Alex and Andre, mixed integer nonlinear programming. You know that these are still out of reach computationally if you want to solve proper large problem to this. So what we would try to do is to have to develop a core of approximation of this in a form of a mixed integer linear programming, in which we develop new linear approximation for the AC power flow equations and branch current expressions. Okay. Those linear approximations take this form. Sorry for bringing some formula in, but it's easy to discuss. So let's say, what are their novelty and striking features? So they are linear in terms of V square, which captures more nonlinearity than something that is linear only in voltage, simple voltage, okay? And so they include second order term then in a form of a Taylor expansion of trigonometric terms, okay? Those are coefficients alpha, beta, and also this can be calculated, and they depend on the point of linearization. Now, we checked this thoroughly first, the quality of this new second order linear approximation for load increases in Baran and VU network, for instance, but this apply to yours based on the results that we obtain. And as you can see here, in terms of the error in terms of voltage approximation is really very, very low. for even for quite harsh load increase, and much better than us compared to a first order linear approximation. We did the same exercise for currents in branches, and if you look at the error in ampere, you can observe the same thing. So those second order linear approximation are much more accurate and really very accurate as compared to first order linear approximations. So then that's good. We could shape our problem and go ahead with it. So the tractable MILP model that we try to solve focus on minimizing the expected cost of distributed energy resources output deviation from some sort of market schedule, okay? And then it's subject to some linear constraints, or there are constraints that you saw in the previous slide on active reactive power balance, branches, and so on, voltage constraints, and so on, and then some constraints that involve integer variables that stems from the modeling of those devices that I mentioned before. Now, in terms of algorithm, sorry, it's a bit, I know it's a bit overwhelming, but I will explain it very briefly. So the algorithm, as I say, it's a sequential linear approximation algorithm. It has two loops, so it's an outer loop and an inner loop. So the difference I will explain it later. So let's go how it works. So at the end, at the beginning, we start with determining the initial point of linearization. So we solve AC power flow for each scenario and periods of time, uncertainty scenario and period of time of the next day, so combination of these. Once we have this, we linearize the model, we build and solve the first mixed integer linear programming model. Then we check if the approximation is trustable. So in the sense that if you foresee that this is a good enough approximation and we don't need to solve again an accurate power flow. If it's so, then we simply take this as a new point of linearization and we rebuild and solve the problem. However, once we feel it's untrustable, it's a tricky criterion that I can explain after in the question session. We solve again power flows for each scenario and period of time. And if the AC feasibility is not met, so then we go again to have a new point of linearization and then loop into it, okay, until we found a solution that is feasible. Now we thoroughly tested this into 3 networks. So it's a 34, so this Baran and Vu, a UK and Portuguese system, in which we consider a number of renewable sources, storages, flexible loads. We consider generally 24 time periods, 10 uncertainty scenarios generated using ARIMA models. Then, as I said, we consider a combination of different forms of flexibility between all these options that we set ourselves: active power curtailment or reactive power provision for renewables, storages, flexible loads, and OLTC. Okay. And in terms of numerical performance, so for these 9 combinations of flexibility options, we can notice in terms of optimality that the optimality gap that measures the distance to the global optimum, it's very small. So the largest one is 0.26 per unit, which is really good. In all cases, we managed to get feasible solutions. Again, this is empirical, so it may not work that well in other cases, but still in that. The number of iterations, so the number of times the mixed integer linear programming is solved, in that case is 3, so 2 plus 1. The times here are very, very good in terms of tens of seconds or so. Well, I would not present the results for the others. There are in our papers that I will show next, but it's time to conclude on this DSO problem. So I would say that we really did a lot of, and especially Muhammad, a lot of numerical experimentation. We don't have a mathematical proof of convergence for that, but regarding solution accuracy, we noticed that the algorithm provides in general optimal and feasible solutions. So optimality gap, it's almost 0%, and I think worst case it was 0.20 something in all cases and under all flexibility options. The solution, this optimal solution, it's obtained in few iterations, and it works even under stressed operating conditions. In terms of computational efficiency, this algorithm is 12 to 30 times faster than competitors like, let's say, mixed integer nonlinear programming solvers. We also compared with different first order linear approximation models, and it still works better. Then when we scale up with the largest system we have, the 200 nodes from Portugal, it still goes below 1 hour, but then again, it depends on how many scenarios and time periods we can plug into it. So there are also some limitations. So for now, it's scalable by extrapolation to grids up to 1,000 nodes, but still distribution network in medium voltage is difficult to find larger networks. And then again, mixed integer linear programming, so it depends also the computational time on the number of binary variables. Okay, so the good news is also that it works well on both radial and weakly mesh distribution grids. So I will move now to the part on the transmission grid, but not before suggesting you for further reading if you are interested in that topic. So we have a number of papers on the problem formulation, linear approximation, and solution algorithms. As Felipe mentioned, so from ATEST, the code source of this method and the datasets will be open early next year, so stay tuned for that. Okay, good. TSO problem. So the features are somehow comparable to the others. So again, we want to help to support the TSO to procure flexibility from conventional generators, renewable energy storage, renewable energy sources, storage, and flexible loads. Again, the issue we have is nonlinear and non-convex constraints that you know very well, power balance equation, thermal limits in lines transformers. In this case, we don't go for mixed integer nonlinear programming because it would be much more complicated. So we approximate the problem as only nonlinear programming. Still, this, when you want to solve very large problems, it's not that easy to solve. And the principles and let's say the main features of the methodology that we propose are the following. So first, we break this down to linear programming models. So this is the core, and we inspire from a nice model developed by that team in reference R. Again, this time the model is linearized also in the V-square space. So having working with V-square again captures better nonlinearity. We use a DC model, but it's more than a DC model because it's augmented with voltage-dependent terms, but also with nodal active power balance equations. We combined all of this with an N-1 security assessment based on AC power flow, ARIMA models to generate renewable scenarios, and then we are using some speed-up techniques in terms of constraint selection and tightening, okay? So we do also a big extension of that model in a reference R by considering contingencies, uncertainty scenarios, multiple time periods, emerging flexible options. As the problem is stochastic, I don't want to get into all these complicated details, but we have here and now and wait AC decisions. And then we also validate it thoroughly under stress operating conditions. Now, when we do literature search on these security constraint OPF problems, the state of the art basically is here. Most people work in deterministic single period, as you can see. There are really very, very few works that takes into account temporal aspects, uncertainty, something more, flexibility. That I think there is only one work of which I am aware, which uses the same features as us, so that goes into, let's say, more comprehensive features of the problem, but still they are used. I think this was developed by the team who developed also math power, okay? But still they are using only DC, whereas we are having a sequential linear programming of the full AC model here, okay? So how the algorithm works, again, I'm getting a bit technical here. We have three main stages. So of course, at the beginning, we have some data inputs, we calculate some power flow, and we activate the algorithm only if there are violations. So then, at the beginning, if you want to solve with a single linearization a problem of this magnitude, it's extremely difficult. You may easily get into infeasible problems or very far from the optimum solution. So what we do, we go step by step. And stage one relies on our, let's say, experience that in general, a DC-based solution is in general able to approximate in a satisfactory way the active power flows in the grid, and this is what we do here. So basically we have a lossless approximation of the whole problem, still linear approximation, but we don't take into account the voltages here. So we kept voltages fixed. At the solution of this, of course, we check with power flows if for each scenario time and contingency there are violation. If they are, we move into stage 2. Here we add into the problem, so we are able to approximate the losses for the first time, but also we take into account voltages. Okay, so we solve again this linear problem. We check if there are constraints, probably there are or not. So then we proceed with step 3. And the step 3 is the only step in which we are doing iteration. So stage 3. So in this one, we start also including tightening, reduction of set of contingencies, and all of those tricks into those, let's say, boxes that I'm not going to explain. Again, I would refer to you to the paper. Now, how it works? We did 2 test cases in the Nordic and Portuguese system. So Nordic system 60 nodes, Portuguese 300 nodes, basically. What we have here, so we model in each of them 10 uncertainty scenarios, 33 contingency for Nordic, 20 for Portuguese, and 24 time periods for both. We choose a number of flexible options here. And of course, as I said, the flexibility, it's active power curtailment, reactive power, and so on and so forth, the one that I mentioned so far. So let's go into some results for the Nordic system and let's say a highly stressed case. So as you can see here, we have these are the initial values, stage 1, stage 2, in the stage 3 with the 3 iterations that it performed. If we look at the total number of violated constraints, you can see that initially we have plenty, then this is getting reduced in stage 1, even more in stage 2. In stage 3, it's generally it reduces, and after the 3rd iteration, it's completely removed. Okay, this is also the time that you get to the solution. Constraints are voltages and power flow limits in both normal operation and after contingencies. Now, if you compare this with IPOP, okay, so in terms of how big the problem is, because this, of course, is the first question that you are going to ask me. How big? So the problem, the NLP problem is that size, so 1.6 million variables, 3.6 million constraints, okay? Then our problem has a little bit more variables and constraints because it's, of course, linearization. This is the solution time that we get for that network. It's around the order of 10 to 15 minutes. And we can see that it's much faster than as we expected, of course, than IPOP. Still, the variation in the objective is small, I would say. For the Portuguese systems, again, I took only the table related to the highly stressed case. Again, we can see the same. So huge number of violations at initial stage, then it's well reduced by stage 2, 3, and iteration 1. Here it converges faster. So in the 2nd iteration of the stage 2, we are already done. Of course, the computational time per stage increases thanks to all of these things. Getting back to comparison to IPOP. So here we have also larger size problems. So for IPOP, it's really quite big. So it's 4.6 million and 10 million variables and 10 million constraints. Still, in our problem, it's solved in around 45 minutes. The objective deviation is still very small, I would say, as compared to IPOP, and the reduction is huge in computational time. So it's really 10 times faster in our case. So I think it's time to conclude for this part as well. So I believe that really for the first time, the most complete and challenging, I would say, uncertainty-aware and flexibility-driven security constraint OPF to date has been solved with acceptable precision and speed. I read it as it is. So again, we did extensive results, and we demonstrate empirically without proof of convergence again, but I think it's a very good sophisticated heuristic. So solution accuracy, we are near optimal, I would say. We are not really on the optimum, but not very far. And I don't believe that an operator will really need or search for a global optimum for such complex problems. We managed to reach feasibility in all cases. In general, let's say the methodology converge after solving 4 to 5 large-scale linear programming problems. Computational efficiency, again, it's 8 to 10 times faster than IPOP. We also did some comparison with alternative linear models. I think our compared better, especially in terms of feasibility. The time, this is the biggest issue. So it's still doable, but I think that as for the distribution system, we are somehow reaching the limits that the programming environment in Julia, as well as the solvers, allow us. So on regular computers, we cannot do more for now. So there is a lot of future work here, scalability. We think how to decompose this and to use parallel calculation. Of course, miracle solution is quantum computers. Again, this is a heavy problem anyway. So if you want to really address such challenging problems, there is no way out. And well, I also look forward to see some reductions in computational effort of this. If you are interested, again, problem formulation, you could refer to that paper. Solution algorithm is this paper published recently in Transactional Power Systems. The code sources for the other tool will be made open in ATEST, so stay tuned, okay? So I'd like to thank you for your attention, and I'm here for responding to any kind of questions. Thanks.
Well, thank you very much, Florin. I would like to thank, in fact, to the three speakers and the three presenters. We have several questions here. We'll not have time to answer them all, but okay, I will start here with the first. So the first is for Alex and Andre. And the question is, how do you calculate if the feasible solution space for the active distribution network OPF with your flexible assets, is it assumed continuous?
Alex, do you want me to take that question?
If you want, okay.
Yeah, so let me answer first about continuous. Yes, in that particular example, we considered only continuous variables. Didn't include any on-load tab changers. There was some binary variables to represent, sorry, this the state of flexible units. You need to differentiate, is it producing power, is it producing P or consuming P? Otherwise, you can get some strange solutions that it's producing and consuming, but overall the space is continuous. And it's an interesting question. It's hard to explain in a few words how to compute these areas, but basically you need to solve OPF model iteratively, maximize P, minimize P, then make some slices or work in different iterative directions to approximate the boundary. There are many papers recently about this. If you approach me somehow, I can share some good ones with you, but the space was continuous. Yeah.
Thank you, Andre. Then we have another question from Rodrigo Vaz, and he asks if this model can be used to plan for growth of protection schemes. For example, insertion of new protection relays, breakers, reclosers, etc. So Alex and Andre.
Well, part of the objective function is the reliability, and that is taken based on basically the consideration of the protection schemes. The one that we used was the one produced by the network company at the time, which is Electricity Northwest here. So following the same approach, we could include the same aspects, although it becomes kind of a parallel calculation. So is not a critical component for the investment. It's basically something that has to be solved in parallel, either offline or iteratively, but it would be computationally costly if we wanted to optimize the protection scheme at the same time.
Okay, so thank you. As I said, it will not be possible to answer to them all, but okay. We have another now for Florin, so the second presentation. Thank you for the presentation. Is there any study for test systems with more than 1,000 or more than 10,000 nodes in terms of scalability? Florin.
No, there is not, as I showed in the state of the art. I think this is the first work to solve the problem of this size. Now it depends how we look. As I said, the computational complexity is related to the overall size of the problem. This is the product of size of the system, number of contingencies that you define, number of uncertainty scenarios, and the number of periods of time. So if you want to go for larger system that the Portuguese that you have, you need to reduce, let's say, the ambition in the number of other dimensions of complexity. So you need to work with less scenarios or less contingencies or less time periods. So for now, we don't have this, but again, you could try to do something for a larger system through decomposition and parallelization, but you need a high performance computer for this. You cannot do it on your regular PC.
Thank you. Okay, another one for you, Florin. Does the method claims feasible solutions even when the ACOPF diverges? If yes, how the results are compared?
Yeah, now it depends. So ACOPF may diverge. Yes, that's true in some cases, even if there is a feasible solution. So this is feasible. We are not at 100%, let's say, good in solving non-convex nonlinear programming problem, for instance. Now, of course, if there is no feasible solution, this algorithm is not doesn't make miracles, you know. But still, we'll try to approach, let's say, the feasible space, and to get closer to it.
Okay, thank you. So we have here more questions. I'll try to answer them directly by here through the chat or so. I would like to thank you once again, Florin, Alejandro, and Andre, and thanks to the audience for attending this webinar. I would like also to stress that all of you will receive the presentations by email. You will also receive more information about the ATEST project, the website, and even the data sets that we already released. So they are open data sets about networks and profiles and everything that we used for these results in these presentations and in others. So you can have access to all of that. And one final thing is that probably the next webinar will also be about ATEST. So we will more or less keep the discussion about ATEST and the remaining tools. So for those that we didn't answer your questions, we will have the opportunity in the next webinar. Thank you very much once again. Bye bye.
Yeah,
Thank you,
thanks.
Felipe.
Bye bye.
Bye.
Bye guys.